Okay, so yeah, I'm just going to be talking about some of the approaches that we've been using with LiDAR for the surficial geology mapping in northern Alberta. And sort of my talk split into three parts. A bit about the surficial mapping program and sort of how it was done in the past. Then really how we're using LiDAR predominantly at the moment. And then finally moving on to perhaps how we will potentially use it in the future. Okay, so the surficial mapping program has been running for a little over a decade now. And it's really a program which is providing sort of base geological data for a variety of purposes. Geological research, the maps are heavily used for geological engineering purposes, geohazard susceptibility, landslide, thermokarst distribution. Mineral exploration, that was the original reason which sort of kicked off this sort of session of mapping. Environmental assessment, and also the surficial maps can help to inform our other sort of geological modeling needs, such as depth to bedrock, drift thickness maps, and feed data into hydrogeological modeling, which we do at a regional scale. Okay, so part of the program has been to really complete the surficial mapping of Alberta. Most of the north has been done in the last 10 years, but there are still some significant areas left, just indicated in by the red box there. Mostly sort of moving across the Chinchaga wandering area and that sort of zone. Now, in the past, and much of the mapping has been done using this methodology. It was really done through a traditional approach, consisting of field mapping, interpretation of stereoscopic air photos. Additional imagery resources were really only used to provide an overview or for navigation purposes. And this process has some problems. It's laborious. It's costly in terms of the digitization process because all of the lines, the geological line work was drawn onto air photos, and in some cases its effectiveness is limited in forest-covered areas, both due to the limited accessibility and visibility of the land surface, of course, which is crucial for the geomorphic interpretations. Okay, so just sort of a few introductory slides. This is sort of the work that we're typically doing in the field, maybe traversing a map area and collecting anywhere between 50 and 400 observations of the geology through natural sections, quarries if they exist, or often just surface mapping with soil probes, that sort of thing, sort of soil pits where we collect samples for mineral exploration. And again, just some of the sort of materials we're mapping: glacial lake sediments, sort of till, aggregate deposits. And then these field observations would be sort of expanded traditionally through stereoscopic photo interpretation to determine the spatial extent of those units. And typically, within a sort of a single sort of NTS quadrant, we may have sort of have to interpret 60 air photos, which would have to be digitized, corrected, and so on and so forth before map publication. Okay, and just an example of the traditional sort of surficial geological map product, which has come out of AGS over the past decade. And of course, one of the major problems of this is just something where we're mapping the composition of the surface in terms of the geological materials at the surface within the upper sort of few meters. Then how can you really have an accurate map in an area such as this, where there's almost no access and no visibility of the landforms? In some areas, the vegetation is useful. It provides sort of indications of the pattern, but still the detailed geomorphological information is sort of on some of the sort of the mineral uplands in this area is still lacking in terms of helping us make an interpretation. So, just to sort of come back to what Robin said, yes, the introduction to LiDAR to this process is, it's really like having the lights turned on. We're mainly interested in the bare earth model, and it really eliminates that vegetation problem for us and allows us to do quite high resolution mapping of landforms and terrain types. And we've been looking at usually from a sort of qualitative mapping approach, but we've also been examining potential quantitative methods to help the mapping process as well. Okay, so some of the sort of things we do, obviously lots of images like this already, but relief shading is the typical derivative product that we would use. But it still suffers from a few problems, but particularly due to when we're mapping linear landforms of a relatively small scale, because their orientation, their visibility is dependent on the chosen sunlight orientation. Just an example, we use a number of sort of processing methods and often to try and reduce this effect. And this is an extreme example taken up in the Edson Hinton area, but just illustrates the effect of different sunlight orientations on the landforms which are visible. There's two sort of streamlined glacial tracks in this image, and depending on the illumination direction, some of those will be visible and some will not. Typically, we will then run a whole series of different illumination directions through principal component analysis and take the first 2 or 3 bands, which accounts for usually about 95% of the variation in that image, and comes close enough to having an isotropic image, which is still intuitive to interpret. Another sort of technique that we use is sort of a sort of a spatial filtering method, which is just smoothing the DEM and then subtracting the original topography from that to highlight landforms of a certain scale. And then that also can form a quantitative metric, which can be used in some analysis that I move on to. And we've also sort of brought in a range of technology to help with this mapping process. All of the Surficial Geology mapping is done using 24-inch tablet displays, so we can map efficiently. Again, eliminates that need for external sort of parties doing any of the digitizing, results in fewer errors, and is considerably faster. And bringing in LiDAR has also enabled us to really take advantage of a sort of a field-based approach to using this imagery as well. So we invested in a number of different tablets, which we can now have all of our imagery on, and can use this. So take our preliminary interpretations out into the field, check them, edit them in the field as we need to. So again, having the right data in the right place. Okay, so just a few examples. This is an area up near Slave Lake, and it's whilst using traditional sort of stereoscopic photos, you get a good idea of the general relief of the landscape. All of the smaller features are often invisible, and this is just a high resolution orthophoto compared to the LiDAR, and you can just, almost looks like a totally different area. There's all of these streamlined tracks which provides directions of ice flow across the upland, all of this sort of topography flanking the upland, which is sort of ice stagnation topography, so where blocks of ice are melting out into the substrate and leaving a different sort of lithological assemblage in those locations. Just at the top, there's an area where we could tell that the sediment was pretty thin. It would basically be bedrock exposed at the surface. So again, that data, it's a qualitative estimate, but we can use that to inform depth of bedrock maps. Just another example. This is sort of again a PCA image, also up in Slave Lake. You can see examples of bedrock fluting, a range of other landforms, which are again, but they were totally invisible on air photos or spot imagery, or even in the field as we're doing mapping at the time. One of the aspects that LiDAR is particularly good at is geohazard detection. It's widely used for landslide detection, and you can see why. Whilst many of the major landslides are detectable through judicial means, many of the smaller landslides and sort of flows can be quite difficult to see in just based on aerial imagery, whereas they are really obviously detectable from the LiDAR image. Just an example of a massive flow coming off the edge of the Swan Hills there. And again, just another example of sort of area affected by lots of landslides, and quite an interesting example, because at the base of these landslides there's actually a little ridge which sort of runs parallel to the contours, and this is an area that's mapped by one of my colleagues. But we think that this is actually where the landslide is being pushed by ice on the glacial lake. So if that interpretation is correct, then these landslides would be 10,000 years old and have been stable since that time. So we also find that we're mapping a much greater area that has been affected by slope instability than when we just use the air photos alone. Okay, just sort of example of the level of detail that we now draw out of the maps in comparison to sort of earlier maps, which are just done through air photo interpretation. You can see sort of a significant enhancement, and also in terms of the accuracy of the map too. We often have difficulties edge matching with older maps, including maps which we had mapped ourselves just using air photos. So the geomorphological information from the LiDAR is of significant benefit. And now all of our map products, we sort of use a blend of a LiDAR relief shade and a slope map, and then have a transparency of a Surficial Geology layer over the top, which I think makes the maps look quite a lot nicer, more intuitive. The user can see the relationship between the terrain and the actual mapping. Okay, so I'm just going to sort of how we're maybe using LiDAR at the moment, but I've also been doing some work into potentially using it for a sort of a predictive style mapping as well. There's sort of two needs for this, in a sense. That one is that whilst there's no doubt that the geological mapping is significantly better than using LiDAR, in some ways it's almost taking us longer to do the mapping, just because there's so much information that we can see, and in some cases it can be almost overwhelming. The second aspect is that whilst we're getting close to finishing this sort of a program of Surficial Geology mapping, in the future we'll likely be mapping in a more thematic approach, and particularly may need to update older areas of maps in a relatively rapid fashion to supply better surface geological information to the geological modeling. So I've been looking at a variety of approaches using really just texture mapping, trying to characterize the relief of areas as a tool to reduce the amount of work that needs to be done to produce these maps. And you've been looking at using a variety of terrain components, some of the sort of typical sort of roughness estimates, other estimates using pattern statistics. There's a whole range of metrics that can be used, and there's certainly more work to be done on this. But and then using an object-based approach to detect some of these landforms and provide a sort of a realistic sort of mapping of these objects. And then finally, classification of those objects into terrain types, which may be correlated to certain types of geological sediment and geological materials. Okay, so I have a sort of a basic workflow at the moment, which involves producing a number of derivatives from the bare DEM, using segmentation to define those objects, and then the process splitting in two and using a classification of the metrics to either define the landforms, or in the areas of the sort of the flat areas, effectively mapping those as organics and using conventional classification of multispectral imagery to establish our peatland types. And then these come back to geological interpretation, reclassification, so manual amendments where needed. So just in terms of the segmentation, the sort of user, we found quite good results by feeding in a number of different metrics which are calculated at different scales, and just on the image on the right is this sort of all of those polygons are being drawn automatically through the segmentation process, and they're really quite realistic to what we would map if we sat there with a tablet and drew those by hand. So that alone is a potentially significant advantage to drawing maybe 5,000 polygons on every geological map that we do. And I first started looking at this in terms of just then doing a simple unsupervised classification in terms of dividing these objects up into different degrees of roughness or ruggedness. But potentially I've moved on to looking at using a supervised approach, using a number of training areas. This sort of the box plots just show some of our basic landform classes. There's colluvium, sand dunes, fluvial, sort of hummocky till deposits, organic and bedrock. And this is an area that we work on from Alberta Lake. And using a variety of metrics, there's actually a reasonably good differentiation of some of these classes just based on the internal sort of textural variations of the landforms alone. There's no information, of course, relating to the context of these landforms or the shape. You know, it's purely based on their internal sort of textural properties. And again, just then using a similar approach to deal with the usually Landsat 7 data in terms of segmenting the image and then just mapping our basic peatland classes into bog and bed in the case. The LiDAR is also important in this respect. We don't look at the details of the canopy or go to any detail into that side, but it's the sort of roughness maps from the LiDAR are useful in themselves to sort of do a cropping effect on that sort of wetland mapping from the multispectral imagery to eliminate the sort of sites that the non-peatland wetlands that you sort of get on uplands, as well as the erroneous classifications that you get from just the spectral overlaps between some of the conifers on Landsat 7 imagery. And then this is an example of a sort of first example of two maps. So this is an area at Alberta Lake, and on the right is the Surficial Geology map, which I mapped a couple of years ago. And then on the left is a map which has been entirely generated through the processes that I described. Now there's a difference in scale between the two, but at a sort of a first order, the results look quite promising. There's a lot of similarity between the maps, and it's surprisingly good actually, given that it's just entirely based on the internal textural properties of the landforms themselves. Okay, so just to conclude, we've been finding that LiDAR has significant benefits for a mapping process. We're certainly getting many new scientific insights from using this in terms of detecting new landform lithological assemblages, significantly improving our estimations of colluvium and areas affected by landslides. Overall, the process is still significantly more efficient. We can reduce the maps related to our own timescale rather than having to sort of hurriedly rush through the mapping process and send air photos off for digitization, which can take uncertain amounts of time. And LiDAR is, I think, particularly in the green zone, is just going to be essential for really current and any future mapping that we intend to do, and it will be essential for improving or increasing our map scale in the future for a more thematic approach. So. Okay, thanks.